When you picture a massive industrial factory floor, I mean, there is just this certain expectation of brute force, right?
Oh, yeah, totally.
You imagine these hulking machines just tearing through thick blocks of steel, and it feels like a purely aggressive process. I think the instinct is to just assume that high-performance manufacturing is, well, all about having a bigger motor or a sharper blade.
Right, because the visual of those thick metal shavings flying everywhere, it really reinforces that idea of raw, unfiltered power.
Exactly. But then you zoom in on the physics of it all and you realize that at the highest levels of manufacturing, brute force actually becomes like your absolute worst enemy.
Yeah, it completely works against you.
It is not about fighting the physics, it is about choreographing them. So today we are doing a deep dive into a really fascinating text on industrial machining.
Specifically looking at CNC lathes, yeah.
Right. We want to uncover why a simple shift in geometry basically changes everything. We are looking at why slant bed lathes completely outperform traditional flatbed lathes.
It is a massive difference in capability.
I mean, we are talking about slant beds reaching spindle speeds of 3,000 to 5,000 RPM.
Yeah.
Meanwhile, flatbeds just struggle, they are practically shaking themselves apart if they try to surpass 2,500 RPM.
Yeah, which is a profound difference in performance for two machines tasked with doing the exact same job.
Right.
Because to achieve those really high speeds, a machine has to overcome several distinct physical barriers that, well, they naturally want to tear the whole thing apart.
And I want to say right up front, even if your daily life has absolutely nothing to do with factory floors, there is a massive lesson here about how we solve problems.
Oh, absolutely.
Because we tend to think we need to fight friction with more force, But the mission of this deep dive into our source material is to extract this engineering brilliance. We want to show how reframing a problem literally, physically changing your angle on it by 45 degrees, transforms chaotic, destructive physics into perfect precision.
It is such an elegant solution to a really violent problem.
Okay, let's unpack this. How can two machines doing the exact same job have such wildly different speed limits simply because one is tilted?
Well, it starts from the ground up.
Right. Before a machine can spin a heavy metal part at 5,000 RPM without vibrating itself into a million pieces, we have to look at its very foundation. We have to look at what the bed, like the base of the machine, is actually made of.
Yeah, so the source text details how traditional flatbeds are constructed. They use what are called bolted joints.
Okay.
So you take heavy, distinct pieces of cast iron or steel, and you bolt them together to form this horizontal base. But in the world of high-speed machining, those bolted joints act as basically boundaries or hard walls.
Hard walls for the vibration.
Exactly. When the cutting tool hits that spinning metal, it generates an enormous amount of kinetic energy, which obviously translates into severe vibration.
Right.
And in a bolted structure, that vibration wave travels through the metal until it hits a joint. But because the two pieces of metal are discrete, the wave cannot flow smoothly across that boundary.
So it just gets stuck.
It gets trapped, it reflects back on itself, and it amplifies.
Yeah.
And this causes the entire machine to ring incredibly loudly and, at high speeds, literally shake out of alignment.
Man, it makes me think of buying one of those cheap, wobbly, assemble-it-yourself bookshelves.
Oh, that is a perfect comparison.
Like, no matter how tightly you crank down those metal bolts, it is always going to shimmy if you bump into it because it is made of distinct, separate parts. The vibration just has nowhere to go but into the joints.
Right. And the slant bed design, according to the text, avoids this entirely. It uses a one-piece casting instead.
So it is just like a solid block of stone.
Basically, yeah.
Huh.
A single continuous heavy iron casting means there is no bolted angle design anywhere in the base for those waves to bounce against.
Wow.
But the geometry is really only half the story here. The material science is just as vital.
Oh, right, the graphite thing.
Yeah. This one-piece cast slant bed uses high-damping iron that is infused with microscopic graphite flakes. Like, the graphite is suspended microscopically throughout the entire iron structure.
I am trying to visualize how that actually stops a physical vibration, though.
Think of those microscopic graphite flakes as millions of tiny internal shock absorbers scattered throughout the iron.
Okay.
When the kinetic wave of a vibration travels through that solid piece of iron and hits a graphite flake, the flake shears ever so slightly at an atomic level.
Wait, really? It shears?
Yeah, and that microscopic friction converts the kinetic vibration into low thermal heat. So the material is literally absorbing the mechanical shaking and safely bleeding it off as a tiny, almost imperceptible bit of warmth.
That is wild. You are neutralizing the vibration at a metallurgical level before it can even travel.
Exactly.
But the source text also highlights the internal shape of this casting, which confused me a bit. There is a hollow hole running right through the center of the slant bed, right? They call it a torque tube.
Yes, the torque tube.
Wait, you mentioned a hollow tube in the center. Doesn't making the iron hollow actually make it weaker? In my head, if you want to stop a machine from shaking, you want as much solid, dense mass as possible.
I know, it feels super counterintuitive to remove material to gain strength, but making it a completely solid block would actually be worse for resisting twisting forces, which engineers call torsion.
Okay, why is that?
So when a massive rotational force is applied like a heavy spindle spinning metal at 5,000 RPM, the structural stress is actually concentrated on the outer edges of the machine base, not the center.
Oh, interesting.
Think of twisting a really thick rubber band. The outer edges stretch the most, while the dead center barely even moves.
That makes total sense.
Right. So by casting a hollow torque tube, engineers basically push the mass out to the perimeter, where it drastically increases the machine's resistance to twisting. Leaving the center solid would just add useless dead weight that does not contribute to the structural rigidity at all.
So it is optimizing where the material actually needs to be to fight the torsion.
Exactly. And that hollow tube actually does double duty. It acts as a natural wind tunnel.
Oh, for cooling.
Yeah, it allows ambient air to flow directly through the center of the massive iron base, which really stabilizes the internal temperature of the machine.
Wow.
And when you combine that hollow tube with the fact that the slant bed has a right-angled triangular cross-section, the metrics from the source are just staggering. That triangular shape boosts the overall rigidity by 20%.
Yeah, the numbers in the text for the peak physical deflection are crazy. Deflection is what measures how much the machine physically bends under a heavy load, right?
Yes, exactly.
A flatbed deflects 0.027 millimeters, but the slant bed cuts that down to 0.012 millimeters. I mean, we are talking about fractions of a human hair here.
Right. A human hair is roughly 0.07 millimeters thick.
So we are looking at a difference of about 15 thousandths of a millimeter. That is almost nothing.
To us, sure. But at microscopic manufacturing scales, that 15 thousandths of a millimeter is literally the difference between an aerospace turbine fitting perfectly or causing a catastrophic engine failure.
Wow. Yeah, so that rigidity is paramount.
Crucially, this massive, stiff structure also shifts the primary resonance frequency of the machine.
Right, because every physical object has a natural frequency where it vibrates most violently if provoked.
Exactly. And flatbeds resonate at around 210 hertz. The problem is, that is dangerously close to the vibration frequencies naturally generated during rapid spindle operation.
Oh, so they feed into each other.
Yeah. If the machine hits that frequency, the vibrations compound and just destroy the tool. But the slant bed's triangular hollow tube design shifts its natural resonance safely up to 320 hertz.
So it moves the machine's physical weak point completely out of the danger zone of standard operation.
Precisely. It is just brilliant engineering.
Okay, but locking down that foundation creates an entirely new physical dilemma because you now have a perfectly rigid object resisting a sharp tool that is violently tearing metal apart.
Right. The dynamic cutting action.
Yeah. On a horizontal flat bed lathe, the tool comes in from the side. The main cutting force pushes down, but because the metal is spinning against a tool coming from the horizontal axis, there is this massive radial force pushing the tool away horizontally.
The spinning metal is fiercely resisting the cut, and this creates a severe 90-degree bending moment.
That bending moment, right?
Yeah, so the cross slide, which is the component actually holding the tool, ends up acting almost like a diving board. The horizontal push from the spinning metal causes the tool to bounce up and down in these tiny micro movements.
And that is what causes chatter, right?
Exactly. Chatter is this violent, destructive vibration that leaves a wavy, ruined finish on the manufactured part, and it drastically shortens the life of the cutting tool.
Here's where it gets really interesting. This is where the slant bed fundamentally changes the geometry by tilting the entire operational bed, usually at a 45-degree angle.
Right.
So instead of tacking the metal horizontally from the side, the tool approaches from the diagonal top. It is like trying to cut a really tough piece of steak on a dinner plate.
Okay, I like this analogy.
If you hold your knife horizontally and try to push sideways into the steak, the plate just slides away from you across the table. But if you stand up, hold the knife vertically, and push straight down from the top, the table absorbs all the force. The steak stays perfectly still.
That is exactly what happens. By coming from the upper diagonal position, the massive cutting force points diagonally downward, perfectly matching the direction of gravity.
It's so smart.
Both the violent cutting force pushing on the tool and the massive weight of the heavy metal workpiece itself are pushed directly down into the thickest, most rigid part of that triangular iron bed.
So these two forces are suddenly aligned.
Yes. Gravity and cutting pressure are actually working together to hold the tool steady. The text notes that this geometric alignment alone reduces vibration amplitudes by another 40%.
That is huge.
Yeah.
And the alignment also affects the heavy X-axis carriage too, right? That is the massive iron block that moves the tool back and forth. Because the carriage rests on this 45-degree slope, gravity is constantly pulling it downward. And the source mentions that this constant downward pull preloads the X-axis ball screw.
Right.
It pushes the internal steel balls tightly against the threads. Does this mean gravity is literally doing the mechanical work of a clamp inside the machine?
It absolutely does. To understand why that matters, think of a ball screw like a spiral staircase where the steps are lined with rolling marbles and a corresponding nut glides smoothly over those marbles.
Okay, I can picture that.
In a flatbed machine, because it sits horizontally, there is always a microscopic gap between the marbles and the threads when the motor changes direction.
And that gap is called backlash, right?
Exactly, backlash. When the machine reverses, it takes a fraction of a second for the gears to catch up and close that gap, which introduces positioning errors.
But on the slant bed,
On a slant bed, the massive weight of the carriage is constantly sliding down that slope. Gravity wedges those rolling marbles tightly against the top edge of the threads at all times. There's zero gap.
so mechanical backlash is just completely eliminated.
Completely. The machine maintains perfect, absolute positioning accuracy without needing complex electronic compensations, simply by letting gravity wedge the components together.
You stop fighting gravity and you basically draft it onto your team.
Perfectly said.
But all of this perfectly aligned cutting force generates an unbelievable amount of friction. I mean, metal tearing through metal at 5,000 RPM creates a massive thermal load.
Oh, extreme heat.
Yeah, and the source shares a startling statistic regarding this. It says 80% of the heat generated during the cutting process transfers directly into the metal chips that are being carved away.
Right. The chips themselves become heat sinks. They are essentially glowing hot coals just flying off the spinning metal.
Wow.
And on a traditional horizontal flatbed machine, those hot chips fall straight down and just pile up rapidly all around the cutting tool and onto the horizontal guide rails.
It is like leaving a thick cast iron pan on a kitchen burner that is only half lit, right? One side of the pan gets scorching hot and begins to expand, while the other side stays relatively cool.
Yeah.
And the metal physically bows and warps in the middle to accommodate the uneven expansion. When that happens to a heavy iron machine bed covered in uneven piles of hot chips, I imagine that thermal deformation transfers directly into the part you are making.
It absolutely does.
But wait, is thermal expansion really that big of a deal for a massive, heavy iron structure? Does it actually warp enough to matter?
Oh, without a doubt. Again, at the microscopic scales of modern manufacturing, that warping is fatal to precision. We are talking about microns.
Oh, right.
Furthermore, the machine relies on linear guideways to move the tool smoothly. These rails require a microscopic, perfectly calibrated film of lubrication oil to function.
And the hot chips just ruin that.
They literally burn away the hydrodynamic oil film when they sit on those horizontal rails. It causes metal-on-metal grinding, accelerating wear, and tearing up the guideways.
So what does the operator do?
The only solution for a flatbed operator is to constantly halt production, stop the spindle, and manually shovel the hot chips out of the way to protect the machine.
Oh man, that is so inefficient. Enter the 45-degree slant bed. It acts like a self-cleaning oven, basically.
Pretty much.
This steep angle creates a natural slide. Gravity pulls those blazing hot chips instantly away from the cutting zone. They drop straight down the slope and directly into a chip conveyor below. They never sit on the machine frame.
Which means they never have the chance to transfer their thermal load into the cast iron. This gravity flow improves heat dissipation by 30%, according to the source text.
That is a huge boost.
And because the chips are whisked away instantly, they never sit on the linear roller guideways, and they never burn away that crucial microscopic oil film.
The text states that continuous high-speed cutting on a slant bed limits the thermal accuracy loss to an incredibly tight 0.004 millimeters per meter.
It's phenomenal.
That is an almost imperceptible amount of thermal expansion for a piece of industrial equipment running at full capacity. And because the heat is managing itself, A factory can run that machine at top speed continuously,
Right, no manual cleaning stops.
which translates directly into increased manufacturing output and, obviously, profitability.
Exactly. So the heat falls away, and the cutting force is stabilized by the angle. This really leaves only one final physical barrier to ultimate speed.
Which is?
The raw rotational violence of spinning a heavy object. The source uses a brilliant visual analogy here.
Oh, the rock on a string.
Yes. Imagine tying a heavy rock to a string and spinning it around your head in a circle. The faster you spin it, the harder that rock pulls outward against your hand.
Right.
That outward pull is centrifugal force. A lathe chuck spinning a heavy metal cylinder at 5,000 RPM generates terrifying amounts of centrifugal force, all of it trying to throw the metal outward and tear the machine apart.
And a traditional flatbed handles this poorly, right? Because it holds the spindle, the heavy rotating part, high up above the horizontal guideways.
Exactly.
In physics terms, it creates a high center of gravity, which basically acts like a long lever. The higher the spinning mass sits above the base, the more leverage that centrifugal force has to wrench the spindle from side to side.
Spot on. That lateral shear force uses the long lever of the machine's height to twist the spindle out of alignment. Over time, and often quite quickly when approaching higher RPMs, this outward twisting destroys the precision spindle bearings.
The machine physically just cannot handle the lateral stress.
No, it can't.
But the source quotes 20,000 hours as the operational lifespan for a slant bed spindle bearings. That is wild.
It really is.
Lowering the center of gravity is not just a trick for achieving higher speeds. It is fundamentally extending the lifespan of the machine's most expensive, delicate parts.
Right.
The slant bed drops the spindle box and the tool turret much closer to the heavy floor. And because it utilizes the massive right-angled triangular cross-section, the outward radial pull is transmitted downward deep into the strongest, thickest part of the machine.
Yes.
It fully protects the advanced motorized spindles and the high-speed ceramic bearings from lateral shear forces.
And this profound structural stability is what allows the slant bed to utilize entirely different movement mechanisms.
What do you mean?
Well, because the slant bed is so incredibly stable against these rotational forces, engineers can actually equip it with fast linear roller guideways.
So what does this all mean? Like, if this machine is dealing with such intense, heavy rotational forces, how can it safely use low-friction linear roller guides instead of heavy bolted friction ways without losing stability?
Well, if a flatbed tried to use low-friction linear guides while spinning heavy parts at 5,000 RPM, the high center of gravity and the centrifugal twisting would likely rip the carriage right off the rails.
Oh, wow.
Yeah, flatbeds are forced to use heavy, bolted friction boxways just to survive the vibration.
Got it.
But friction boxways suffer from a phenomenon known as stick slip resistance.
Stick slip.
Yeah. Think of trying to push a really heavy wooden crate across a rubber floor. You push, but static friction holds it in place. It sticks.
Right, until you push hard enough.
Exactly. You push harder, the friction breaks, and the crate suddenly jerks forward. It slips. When a machine motor tries to move a heavy friction way exactly 0.001 millimeters, the static friction might hold it back.
So the motor ramps up power.
The friction breaks, and the carriage jerks forward 0.003 millimeters instead. That stick slip creates severe positioning errors and makes the machine slow and clunky.
Oh, I see. But linear roller guides, on the other hand, are like putting that heavy wooden crate on ice skates.
Exactly. They roll flawlessly with almost zero static friction.
And the slant bed can use these fast, low-friction skates because its right-angled triangle geometry and its low center of gravity completely neutralize the twisting forces before they ever reach the rails.
You got it.
The heavy lifting of stabilizing the machine is handled entirely by the cast iron shape and the force of gravity. This frees the linear rails to do nothing but glide.
Which is a huge advantage.
As a result, the tool can dart around the metal with lightning-fast agility, completely free of stick-slip resistance. It makes the slant bed absolutely excel at high-speed, high-precision batch work.
It is the ultimate synthesis of material science and geometric design. By aligning the dynamic, violent forces of the machining process with the natural passive force of gravity, the slant bed completely eliminates the destructive chaotic energy that holds the flatbed back.
Yeah.
A slant bed lathe does not run twice as fast because it relies on a more powerful motor. It runs faster because its triangular iron structure with graphite shock absorbers, its downward force alignment, and its gravity-assisted chip slide all operate in perfect, elegant harmony.
It neutralizes the vibration, the thermal deformation, and the centrifugal shear forces simultaneously. This is just a masterclass in systems thinking.
Truly.
It proves that when you stop fighting nature, when you stop trying to bolt down hard walls against friction and vibration, and instead start designing with gravity, you do not just solve one isolated problem. By physically changing your angle, you solve all of the cascading problems at once.
It's the definition of working smarter, not harder.
Exactly. Working smarter is quite literally built into the geometry of our most advanced tools, which leaves us with a really fascinating thought to ponder.
Yeah.
If simply tilting a machine's geometry 45 degrees revolutionized its speed, its thermal management, and its longevity just by working with gravity instead of against it, what other systems are we dealing with that are basically flatbeds?
Oh, I love that.
Right. Think about your rigid workflows, your organizational structures, or the daily routines we constantly force to work against the grain. What chaotic friction could we eliminate in our own lives simply by shifting our orientation and letting gravity do the work?